So. Yeah, this is the only upgrade we can get nowadays.
Yes.
Okay, great. So, okay, I think, let me share the,
So. Yeah, this is the only upgrade we can get nowadays.
Sorry, now I'm muted because I have to. Okay, great. So let me start. First of all, thanking everybody to be here once again to the online SPICE-SPIN+X seminar series. This is run between Spin Phenomena Interdisciplinary Center SPICE that I run together with Karen Evershaw-Sitte, who is in Mainz, but we'll be moving as a W3 professor in Duisburg pretty soon. And the collaborative center SPIN+X between Kaiserslautern and Mainz, led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe, who are here among the panelists. And as you all know, this is a webinar format. Please write your questions down to Q&A, and after the talk, I will give you the floor to ask questions to the speaker, Claudia, in a minute. And please check out the next speakers. We have a very nice lineup of future speakers going on, probably all the way to April and probably beyond. Today's speaker needs no introduction. She's probably the most famous woman in our field, on any field probably. Claudia Felser, director of the Max Planck Institute, but in reality, her work is in Dresden, but her heart is in Mainz, which is very nice to know. Exactly. So she's designed and discovered many novel, interesting compounds and materials in the very broad family of Heuslers. So anything Heuslers, she's the queen or the empress of Heuslers, and justifiably so. She's had huge list of accomplishments and a very it's been neidisch nach diesem Liste, this super list of accomplishments that I won't even bother read them. You can see them there, and it's a wonderful pleasure to have her here with us today to give us a talk. So go ahead, and Claudia, and start sharing your talk. Perfect. And I'll mute myself, and then go ahead.
Yeah, thank you, Jairo. Thank you very much for the kind invitation. And as everybody knows, my heart is always in Mainz and Kaiserslautern. So I had a wonderful time in Mainz, Kaiserslautern. And therefore, and I have to say that my daughter is now back in the area, so which tells you also that I really like very much to be there. And I'm happy to talk today about magnetic materials and their relation to topology. And this is a collaboration with many people from my group. So I think I want to remind you, since there are also students here, that topology is a new concept in condensed matter physics, and where we go beyond symmetry, which you will learn soon, and which determines interesting properties in materials. So, so it's quite a simple concept from mathematics, and it simply determines the surface of a material. Like here's this Berliner, in Germany we call this Berliner or Pfannkuchen. So this has no hole, it has this round surface like a ball, and it has the same topology, for example, like this object. And it's different from the topology of a donut, which has a hole here, and the topology is the same as the topology, for example, of a coffee cup. And this is very often nicely shown in an animation. But I have here this drawings now. And since we are in Mainz, we all like brezeln and we go to Dietsch. So you maybe prefer this topology if you go to the bakery, and this has a similar topology because it has 3 holes even than this object here. So this can be transformed into an electronic structure, into the band structure. And here is a simple sketch, and I want to explain this. We have here, for example, the valence band of a semiconductor and the conduction band, and we have a band gap between the conduction and the valence band. And we know the band gap depends strongly on the bonding interaction, because we can also say these are the occupied states and these are the unoccupied states. And if the bonding is very strong, I have a very big band gap. Depending from the bonding strength, I can have also an overlap between the two bands, like here, and depending then from the symmetry of the bands, if they have the same symmetry, if they're, for example, both S bands or parity, so this becomes a forbidden crossing, and becomes a forbidden crossing, and it can open up a band gap. But there are other cases, even if they have the different orbital character like S and B, if we have spin-orbit coupling, this can also become a forbidden crossing and open up a band gap. And then we have a part of the conduction band which has a different symmetry, for example, in the valence band and vice versa. So this is symbolized here. The trivial normal semiconductor is symbolized by a donut, and the inverted here, the so-called topological semiconductor, is symbolized by a Möbius stripe. This band inversion is very common in materials which have heavy elements, because there the outer s electrons, the 5 or 6 s electrons, are contracted due to the high speed of the inner s electrons, the 1s electrons, and this is also reflected in the valence of heavy elements. So here are the examples from the group 3, for example, indium and thallium. The light elements like arsenic and phosphor, they have the valence 3 plus 3, while the heavier elements have only the valence plus 1, because they like to keep the s electrons closer to the core and they stay occupied, which means they become a part of the valence band instead of the conduction band. And this leads here to this interesting effect, this so-called what we call inert pair effect. And this is also the reason why we have so many materials which are topologically interesting. So from all the inorganic materials which we know, they are all in a database with their structure. They were all investigated recently and characterized by their topology. And it's known from the 250,000 inorganic materials that more than 20% are topologically interesting. This is quite a big number, and it explains why this field is such an active field, because still there's a lot to do and there's interesting physics to discover. So recently, in another paper, we started to work on antiferromagnetic topological material with high throughput calculation, and we used this, the materials which were used here in this study were always the materials which were already determined. The antiferromagnetic structure was carefully determined, so there were neutron data there, because this is always a very important precondition. If we want to do a topological characterization, we really need the crystal structure study very careful. So if you go now to websites, so there are several websites, and this is the website from Andy Bernowicz and our team. So you can find all the materials you are interested in, all this, most of this 250,000 materials. So far, they are mainly the non-magnetic materials, but we are changing the database day by day. And so you can click simply on the periodic table, and then you see immediately here, for example, on hafnium and tellurium. And then you see immediately the different compounds, their symmetry group, and their topological indice. Here you see, for example, that hafnium telluride 5 is a topological insulator with the following indices. This material is recently really under heavy investigation, because it shows in a 3D material a quantum Hall effect and even a fractional quantum Hall effect. So there are many different topological materials. I showed you how to determine the topological insulators, and I simply want to show you really how diverse this material can be. But there are also semimetals. I will be in the second part of my talk. I will talk about the semimetals. I have not the time in this talk to talk about this new fermions. But you see, the materials contain very often heavy elements, and they are of very different compositions. So far, most of the materials are binaries, because they are much simpler to make, but there are also ternary compounds and even magnetic compounds. So in the new study of the antiferromagnetic topological materials, we could put a certain aspect, certain materials together under a certain aspect. So this was the groups which were under our investigation, and some you are familiar of and you know from other in a different context, and they are also well-studied material most of the time, because therefore they had their neutron data and their spin structures available in the database. And I think we have to study even more materials in the future by doing neutron investigation to get even more information. But here you see, for example, that some of the iron pnictides are topological materials, and their chromium counterparts. And we also investigated the manganese, for example, counterparts with similar structures with the same kind of square lattice like the iron pnictides. So these compounds are also discussed in work of Gyro, and one very famous member is the copper manganese arsenic. Here in the orthorhombic study, this was one of the very few first studies on antiferromagnetic compound, which was shown that they show the semi-metallic behavior. You see, it's not an insulator, what I explained on my first slide. It's more here because I hope you see it. I have a little bit of problem with Zoom. You see the crossing point. But there's a big family and many relatives of this, like also the strontium manganese bismuth 2 and other members which are related to the iron pnictide. And many of them have this crossing point around the Fermi energy. So this is a rich family where we still can investigate interesting properties. So we very early worked on another class of material at the time in 2012 with Shushen, while we were looking for new topological insulators, and one potential candidate, plutonium telluride with the sodium chloride structure. Here's the sodium chloride structure, shows this interesting band inversion, which I explained at the beginning. So it's an inversion here between the 6D states and the 5F states. This is very interesting because these are all materials in this group of materials which you can see here, which have F electrons, so they are strongly correlated, and they are one of the few already investigated or verified materials or investigated materials where you where the topology is driven by a strong correlation. So this is, I think, the direction we go nowadays. We look for many, many more of this kind of materials. And here you see the scheme of the band inversion. And then the nice thing is, if you identify a material which is topological relevant, so the first thing is what you do a band structure calculation and you look for the band structure, but then the next step is you do a surface calculation and you look whether you have a surface state. And here's the example for plutonium telluride. So the bands are the deep red ones, and here you see nicely this, you have a gap around the Fermi energy, and you see nicely this crossing point, this Dirac kind of surface state. So this is really a topological insulator, and it's known that plutonium telluride under pressure can even have a band gap of 0.4 eV. So you have really a nice topological insulator. Unfortunately, there are not so many people who want to work with plutonium. The same is one example from the recent paper, from the Nature paper with Andrei Bernovic. So there's a higher order topological insulator identified in this neptunium compound. And it's again, not something which is easy to study. But you see here that also holmium phosphide or more conventional and uranium compounds, which are also easier to study, are examples for this antiferromagnetic topological insulators. Another example where we were very much interested and on which I worked with my old friend Jürgen Kübler, with whom I did many nice work, and he's still working with me despite of being 84, and people in Kaiserslautern and Mainz, I think they know him also from our nice collaboration, because he started the collaboration in Mainz times in the context of Heusler compounds. And here was work on this manganese 3X compound. So Alan MacDonald predicted a non-collinear spin structure, and anomalous Hall effect in manganese-3 iridium and manganese-3 platinum. At the same time, when we were investigating manganese-3 tin and manganese-3 germanium, and we also identified here a non-collinear spin structure. Nicely here, in this case, we could even see that we have here a Dirac, a white semi-metal with manganese-3 germanium and manganese-3 platinum, and we really could show the anomalous Hall effect. You can say, I didn't explain you so far the anomalous Hall effect, but everybody knows that gyro is very famous for the anomalous Hall effect, and I will explain you the anomalous Hall effect in a different context. But until this time in 2014, people believed that antiferromagnets cannot have an anomalous Hall effect because it was believed that the anomalous Hall effect scales with magnetization, and if the magnetic moment is 0, the anomalous Hall effect should be also 0. But here in this measurement, you see the anomalous Hall effect, you see here in Hall measurement as a function of the magnetic field, and you see here this nice jump in the anomalous Hall effect in the manganese germanium and here in the manganese-3 tin, which is a nice, and it's a giant jump. Experimentalists who are working on this kind of materials know that this is a really large effect, not a small effect. This cannot come from any impurity in the material because really it's a giant effect compared to the magnetization. Anyway, so despite of the topological insulators, which I gave you in magnetic topological insulator, I gave you a brief overview. Recently, semi-metal become in the focus, and I already mentioned in antiferromagnetic manganese-3 germanium, that this is a magnetic semi-metal. So since this is in the focus nowadays of topological material, I want to come back and discuss this a little bit more in length. So there's this very nice painting from Clay, which I still like to show because I always enjoy it, that he already thought about Dirac crossings in art. And here we even have Dirac points at the, or crossing points, Dirac point at different energy, which could be only realized in nice chiral crystals. So he already has foreseen a lot of interesting physics in his painting here. So this Dirac crossings, this degenerated points are quite common in materials and even more common in also in ferromagnetic materials. So because as soon, this is a very nice picture here from Roy Hoffman, who did this for a chain of hydrogen atom. As soon as we have 2 atoms in a chain, so if we draw a band structure, for example, for hydrogen, for 1 electron, for example, we know we do this in the exercise in solid state physics in the basic course. So we have here this kind of band structure. And if we have 2 atoms per unit cell, we have to fold back our band structure. And then we end up with this degenerated point here at the Bryan zone, which means, so this is not a rare case that we have this degenerated points in materials that are quite common. So therefore, it's not surprising that we have many materials which shows these features. But you will see that this will have even impact beyond of the beauty of topology and writing a nice paper. So there might be even very, very interesting effects there. So I simply want to explain what is the origin of this crossing point. So as I explained before, so we can have a situation that we have a material where we have a valence band and a conduction band. And in the semi-metal, we can have this overlapping region. So this region is a nodal line here, for example, and depending from the symmetry of the bands and the symmetry of our crystal. So if we apply spin-orbit coupling, so spin is not a good quantum number, we can have a situation that this become a forbidden crossing and it open up a band gap and we get a topological insulator. So this is a 3-dimensional version of the electronic structure I have shown you before. So now you can imagine this is my crystal. It's an insulator in the bulk because we have here this nice band gap. This can be plutonium telluride or bismuth selenide. And then we have on the surface this nice Dirac cone I showed you in plutonium telluride. The surface state, you might remember, this is now this 3-dimensional visualization. And here you even see the spin structure of the surface state. So my crystal is insulating in the bulk, but has this very beautiful surface state. So this is protected because it's a topological material, and the properties and the surface states come from the bulk. So it's really related to the bulk. So if I destroy the surface by surface reconstruction, or I put water on my plutonium telluride, the plutonium telluride probably would oxidize. Then the surface state simply goes a little bit into the bulk and separates now the plutonium oxide from the crystal, but it still stays there because it's a property of the topology of the crystal, because the surrounding has a trivial, like the vacuum, the universe has a trivial topology, and therefore we have this topological surface state, which we even see nicely in DFT. Nothing magic behind this. It's simply also the result of a DFT calculation. So, but what can also happen, depending on the crystal structure, that some of these points in the reciprocal space, the space of the electronic structure, are not forbidden. So we can we can stay here with some points, and this point can be at high symmetry points in the reciprocal space or at low symmetry points. And depending where these crossing points stay, we have Dirac semimetals or Weyl semimetals. So Dirac points or Weyl points here, if we talk about the points. Here, then you can have these points. These are points in the electronic structure of the bulk. So the crystal is now a semi-metal because we have still electron density here between the occupied and the unoccupied states. So we have a different electronic transport. It's not an insulator. And therefore, these are the bulk properties. And due to this bulk properties, we can have also a surface state which has also a very, very special spin structure. So as I said, we can distinguish between Dirac and Weyl points. So Dirac points are 4 times degenerated, and they are at high symmetry points. We know this from graphene or from my nice simple picture here. So this is, if this is at the center at a special point in the Bryon zone, this is easy to find. And like in graphene, we have exactly the point at the K point here. So then we have it at this high symmetry point, it's 4 times degenerated. If we would now strain our graphene, we would lift this degeneration and would end up with two 2 times degenerated points, and they are Weyl points. And the nice thing is of this Weyl points is they have chirality, and they more or less act like sources, or like a source and sink, like magnetic monopoles. So there are 2 ways to transform a Dirac point into Weyl points. One is simply I strain my graphene, which will be not so easy because it likes to be Dirac and doesn't want to become Weyl. Or we can make something magnetic, because then we break time reversal symmetry. And this is the second condition, despite of we have no inversion symmetry, we break time reversal symmetry, we have a magnetic material, or we apply magnetic field to lift this degeneration and turn the Dirac point into 2 Weyl points. The interesting thing is, what I still think most of the people in material science and people who are interested in materials don't recognize that all the crossings in magnetic materials are Weyl points. So Burkhard now can imagine on which class of materials I'm now working after I worked on Heusler compounds, because we had always in our Forschergruppe Heuslers and double perovskites. It just shows the same properties. Anyway, I don't want to say too much, otherwise I get into trouble with my group. Okay, good. So if you have this crossing points as Weyl points, you see many, many interesting properties. And this is now really confusing, you see, so you can measure a lot. But most of the time, these measurements are transport measurements. So you simply use your PPMS, your physical property measurement system, which you buy from a company. And so you contact your crystal and you apply magnetic field, you apply temperature gradient, and I measure the resistance. So I can already measure very, very many interesting properties. And on this side, you see some of the crystals, and all these crystals are topologically magnetic properties. I already told you a little bit about manganese-3 tin, which is this non-collinear antiferromagnetic material for which we already did a lot of this measurement. So I want to guide you through this complex measurement. But the first thing, and you maybe understand from what you learned already, is what we do first is like, if we have grown our crystal, we investigate angle-resolved photo emission, because this is a method which we can check whether the calculated electronic structure, which we did with density functional theory or even beyond, if we have here this magnetic and correlated systems. So we check whether the calculated electronic structure is really the experimental electronic structure, because it doesn't make sense to measure something if we have not proven that our calculations are correct. The same we can do with STM scanning. Here's this measurement as a second method here with this scanning tunneling microscopy measurement. You see exactly the same information as you see in uppers. And then we do our transport measurement to investigate all these interesting properties. So why am I so excited about the Weyl points? And this is really because I think the Weyl points have this, what I showed you before, you remember, they have this special behavior. So they behave like a magnetic monopole, like a sink and a source. So this gives very, very special properties. It's one solution. The Weyl equation is a solution of the Dirac equation. So again, we have relativistic effects taken into account. So we always do our calculation also full relativistic. And the solution was done for high energy physics. And you find even the information in Wikipedia, which I think is always very funny. The first measurement what we do in transport is to look for the so-called chiral anomaly, which is a special solution of the Dirac equation, which was invented by Weyl. So if you have, and later also by other people who have done this very careful mathematical investigation, that you can have the situation that depending from how your experiment is, that you can find an anomalous non-conservation of a chiral current. So originally it was done for understanding the asymmetry between elementary particles and antiparticles, but nowadays we do the same for electron and holes in the semimetals, because the semimetals, they have all these crossing points, and so we always are close to a compensation point also between electron and holes, and we find very often this interesting properties which were originally predicted for high energy physics in crystal. So this is now the recipe. What we do if we want to investigate Weyl semimetals, we look first for the surface state, which you see here. It's the so-called Fermi arc, which you saw in my first figure 2. This is like you have this very special doubly degenerated Weyl points in the crystal at non-high symmetry points, and then on the surfaces points are connected by Fermi arcs. So we have to find first the Fermi arc to see, and the bulk electronic structure. The next thing is then we investigate the intrinsic anomalous Hall effect and the chiral anomaly, and this is done by electrical transport. So we apply a magnetic field in parallel to the electric field. In a normal Hall measurement, we see a different property compared to the situation when we then apply the magnetic field parallel to the electric field. So we see the so-called chiral anomaly, which is a negative magnetoresistance effect in this material. So this is more or less a smoking gun experiment, and these are related to an extra contribution to the Maxwell equation due to in this Weyl semimetal. And instead of an electric field gradient, we can also apply a temperature gradient. So we like to measure thermoelectric properties also of the material. So we would see a related effect, which is the so-called axial gravitational anomaly, which was predicted from Subier-Sachdev and others, and was already also investigated in bismuth. I think Jörg Herrmanns already reported about this, even at room temperature in antimony doped bismuth Weyl semimetal, so you maybe have heard it before. Otherwise, we see also very big responses to other external stimuli, which I think personally is very interesting, which is like a giant anomalous Hall effect in magnetic material and a giant response on the Nernst effect. So we really think that this is a new way to find new materials for energy conversion, which are going far beyond what we know from thermoelectrics so far. So we start with one material, and we start with my most favorite class of materials. And luckily, we have Weyl points in cobalt to Heusler compounds, and therefore I can continue with my work from old days. And I'm sure, I think, even I learned a lot in old days, I have to say, because we did already anomalous Hall effect measurement, not me, but Gerhard Jakob on single crystals of cobalt manganese gallium. So I want to remind you, but I think this is like what we call Eulen nach Athen tragen, ne? Because the family of Heusler compounds is well known in Mainz and Kaiserslautern. And you know that we have two groups of materials. The half Heusler compound, which has the composition 111, and the full Heusler compounds, which have the composition 211. And you can use many different elements to build up these crystals, and you find many good magnets, because at the end of the day, as I told you, we want to see this giant response, like a giant Nernst effect. We want to have it at room temperature or even higher. So it's good if these materials are magnetic at room temperature. And this is the case in case of Heuslers. And I think I don't also have to explain in length that Heusler compounds are so-called half-metallic ferromagnets. So we can have Heusler compounds which are semiconductors, even with so many different elements, and even with magnetic elements in the material, like iron, 2 vanadium. Aluminium is a non-magnetic Heusler compound, even semiconducting, for example. So this is simply by counting the electrons, like we have 3, 5 semiconductors, and mercury telluride is a semiconductor. If you have a closed shell system of all the valence electrons of the material, we end up with a semiconductor. And this is surprisingly even for iron, 2 vanadium, aluminium, for example. In the Heuslers, we have to count then simply the electrons, like here are examples, and I want to start here with cobalt manganese gallium, since this is a compound where we have a focus on. So we have cobalt, which has 9 valence electron, manganese, which has 7 valence electron, and gallium is in group 3, has 3 valence electrons. So in total, we have 28 valence electrons. So for the iron, vanadium, aluminium, we have here 12 in each spin direction, which means we fill up this closed shell electrons. These are 24 electrons. And then we have 4 electrons on top, because 28 minus 24 are 4 electrons. And this is exactly what we measure as a saturation magnetization in this compound. And these are exactly these leftover electrons, which are here in this half metallic ferromagnet, which is half metallic, semiconducting in one spin direction and metallic in the other spin direction. So these are the 4 electrons here, and these are the formula. And you see, so this you can read even here on this graph. So we have 28 valence electrons and formula saturation magnetization, and these are experimental data of many of the cobalt Heusler compounds. So they are all lying on this half metallic line, and there's nice work done in Mainz also on cobalt manganese silicon, which has even proven that this compound shows there's some evidence in Engelhauser photoemission for half metallicity. Anyway, at the same time, TC is quite high, which means so the compound is ferromagnetic below this ferromagnetic to paramagnetic transition. So TC is very high, so these materials are really interesting. So in 2017, so people recognized that crossings in ferromagnets are Weyl points, and Andrei Bernovic and his team recognized that this half metallic ferromagnet, they have not so many bands around the Fermi energy, like here's this cobalt 2 titanium tin, and they recognized, look here, nice crossings nothing special, but they recognize there are crossings in Heusler compounds, and they wrote a very nice paper, and others too, predicting that this are magnetic Weyl semimetals. And this was really exciting at this time because people were looking for magnetic Weyl semimetals, but they didn't find. They predicted something in iridates, but iridates, these are oxides, and in reality they were insulating and antiferromagnetic, so instead of showing semi-metallic behavior. So everybody was happy, but we decided to work on cobalt to manganese gallium, because this here you see, sorry, I forgot to say, here you see this crossing points. Here is the Fermi energy, the energy which separates the occupied from the unoccupied bands, and these are the electrons which are interesting for transport, but these points are above the Fermi energy, so we recognize this is maybe not the way to go, but we have known that manganese 3 gallium has also Weyl points at the Fermi energy, so we looked for this material, checked in Ingerosa photo emission whether our band structure is correct, looked for the anomalous Hall effect and the anomalous Nernst effect in this compound, and I want to explain you now in the following what does this exactly mean. So in cobalt 2 manganese gallium, so as one example of the Heuslers, we have many mirror planes, and we have a cubic symmetry, and we have an FCC lattice here. If you see it from the perspective only of one color, easily visible. And since it's cubic, we would have, if we would try to draw this overlap between the conduction and the valence band, we have, because of the cubic symmetry, nodal lines in X, Y, Z direction, and this leads to this feature, which are the nodal lines in this compound. So if we apply now a magnetic field, and with spin orbit coupling, we can turn some of the nodal lines here, as for example, into Weyl points, which you can see here. So, but in reality, this material is also a soft magnetic material. So in a photo emission machine, we cannot do this. Therefore, our plan was only to see here in this compound, the nodal lines. So, and this is exactly what we did together with Hassan. So we made films and single crystals, and his team investigated here the bike electronic structure. And as you see, nice, here's this crossing points, but the crossing points are a series of crossing points. It's a nodal line along this direction, which you can see here. Here we investigate the XY plane, and the prediction also, if you have such a nodal line ferromagnet, was that you would have some surface states which are more complex than simply Fermi arcs. You find this kind of drumhead surface state, which are in nice agreement with the calculated prediction of the surface state, which tells us also that here a simple density functional theory calculation for the Heuslers works quite well. So then we investigated the transport properties, and you know, we do Hall measurements for this. As I said, we use a single crystal, put it contact the single crystal, put a contact on the single crystal, and then we measure the resistivity in a magnetic field in a Hall setup. And this we do normally for all our normal topological semiconductors. In case of magnetic material, so we have this intrinsic magnetism in this material, so we measure an additional contribution to the Hall effect, and this is the anomalous Hall effect. So this is what I show you in the following slide. And the anomalous Hall effect, I think we have very nice reviews. And so this is like in 2010, in this nice review with Nargosa, Gyro, and McDonald, and Ong, and Onora, it was already described that the Hall effect goes with the Berry curvature. And thanks to my collaboration with Jürgen Küppler, he always was already early interested in the Berry curvature. So we calculated also for many of the Heusler compounds the anomalous Hall effect based on the Berry curvature. So this was also which explains the anomalous Hall effect in this non-collinear antiferromagnetic material, because they have a Berry curvature despite of having a zero magnetic moment. And this is already old work, and which was done in the context of nice measurements of Gerhard Jacobs' group at this time in thin films. They found out that cobalt to manganese gallium has a giant anomalous Hall effect. And at this time, it was a big question mark, why? So together with Jürgen, we worked with DFT on this, and we did Berry curvature calculation and calculated the anomalous Hall effect. And here you see this nice crossing point in cobalt to manganese aluminium, which is isoelectronic to the gallium compound. Later we published the gallium compound out also. And you see that there's a very nice agreement with the measured and the calculated anomalous Hall effect, which was published at this time without really understanding. In 2016, we finally understood, after all this knowledge about Weyl semimetals crossing point and the contribution of this crossing point to the Berry phase, Berry curvature, that this is the origin. Here you see the Weyl point in cobalt to manganese gallium and this nice peak here in the Berry curvature in this compound cobalt to manganese gallium and cobalt to manganese aluminium. So this explains this really enormous high value in the Berry curvature, which is unexpected high. So then recently in my team, we did some toy model calculation to really understand this. What are the contribution, which are for finding fingerprints, also to find more materials which show giant anomalous Hall and giant anomalous Nernst effect. So we simply did it for the case of Weyl points, for example, and then you see that you get these peaks in the Berry curvature, which then leads to an anomalous peak in the anomalous Hall conductivity. And since the Nernst effect is the first derivative, so we see also a giant response in the anomalous Hall, Nernst. And this is here's a measurement. So we have cobalt to manganese gallium also having a giant anomalous Hall angle, which is here the anomalous Hall effect over the charge carriers, and which is much larger than in many other topological material and even other materials, which we would expect 100% for a quantum anomalous Hall effect, which tells us also that we are maybe being quite close in this material for potential quantum effects in this material. So the spintronic community would immediately ask, so did you really look? There are also extrinsic contribution to the Hall effect, and they are even related to the Berry phase. And indeed, if you look here in this famous diagram, you see that cobalt to manganese gallium lies here in this intrinsic area. So you can also measure it as a function of temperature, so that this here mainly the intrinsic properties play a role. So we also measured the Nernst effect in this material, which is really large. If you see here the value of 8, and if you see it as a function of temperature, you see it increases even above room temperature. And if you know the TC of this material, which is like 800 Kelvin, so you can expect that the value will go even up to 8 to 10 or 12, which is much higher what you would normally expect if or see. It would lead to a higher figure of merit than normal thermoelectric materials. So you simply can compare it here to a figure which was also done by our Japanese colleague. It's much higher than what you expect this as a function of the magnetization. So it looks a little bit linear, but then if you look closer here, especially this material with the crossing point, cobalt to manganese gallium, but you see also manganese cobalt, manganese 3 tin, which I discussed in the beginning, shows also a giant response compared to the tiny little moment you see in this material. So it's orders of magnitude larger. So this has led then also to very systematic investigation of Nagasuchi's group on iron. So he simply looked for cheap and available elements for really application in to use the Nernst effect with this concept, also looking for crossing points, Weyl points, and nodal lines in magnetic material. And I simply can say this is only the tip of the iceberg so far. There are only very few magnetic materials investigated, and I assume in many other big classes of materials there might be even more interesting Nernst effects to find. Okay, so Then as a second example, I want to talk about this cobalt-3 tin 2 sulfide 2. So it's simply, I repeat what I explained. We show APES, we show the anomalous Hall effect, but we also show APES here. I have to say the chiral anomaly, we show APES and SDM measurement, and we show the Nernst effect for this material too. But you know already, why do I do this for a second material, and why does this material even draw more attention than the cobalt-2 manganese gallium? This is because this is a quasi two-dimensional material and it's a Kagome lattice. So people who are in correlated materials like Kagome lattice, and this area of research has started with some very nice work of Joe Szekilski from MIT, when he proposed that iron 3 tin 2 has this very nice ferromagnetic, is a very nice ferromagnetic Kagome metal, which has a Dirac cone because of symmetry of the crystal in the material. And additionally, nowadays, it's also known that in this ferromagnetic Kagome lattice, we don't have not only these crossing points here, we also have flat bands here, which are even more interesting in the community of correlation. Anyway, so we thought we like our cobalt, and cobalt-3 tin 2 sulfide 2 is even nicer because this compound shows out of plane magnetization, and therefore it's hard magnetic. I told you we couldn't see really the Y points in cobalt-2 manganese gallium because it's a soft magnetic material, so we cannot apply magnetic field in an APES machine. So we thought, oh, let's do this compound. So we could grow very nice single crystals, but also nice shape-like crystals, which were also a very nice starting point. So we looked in the electronic structure, and this compound has a quite simple electronic structure. It's more or less exactly what you want to have in the ideal case. You have two bands crossing at the Fermi energy, and they cross with this nice crossing point. So we have this nice Y points, ideal Y points, and you see this is, if you, the red lines is spin up. So if you don't apply spin orbit coupling, and the greens are if you apply spin orbit coupling, so you have this very nice crossing points around the Fermi energy. And you have a quite simple Fermi surface because of the simple electronic structure. So this compound is a relative of a semiconductor. It has one additional electron. What you see here is just one electron here occupying this band, more than the semiconducting counterpart. And here you see the drawing of the nodal lines in this compound, and here's Y points and the Y points here in the Bryan zone in this material. So the smoking gun experiment, which we didn't plan here on this material, but which was forced by the editor, was like we should show the chiral anomaly in this compound, which means we should have a positive magnetoresistance effect when the magnetic field is perpendicular to the current, so a normal Hall measurement, and it should be a negative magnetoresistance effect when the B field and the current are in parallel. And this is what you observe in this material. So one smoking experiment is done. And then we compared the surface state. So this is the calculation of the surface state in this compound. This has giant Fermi arcs. The Fermi arcs in this magnetic materials are much larger in the non-magnetic material, so which also explains this unusual transport properties. And these are now here the APES data, and you see nicely how you can see this Fermi arc surface state in this material. We did also SDM together with Heim, Beidenkopf's group, and here it depends from the termination. So this is a tin termination. In the tin termination, we see also this Fermi arcs, and in the cobalt termination, we see Fermi arcs. In the sulfide termination, we don't see Fermi arcs. So, but to investigate also the Y points, you see, I have here the pictures of all the audience. So we had to dope the surface with potassium to move the Fermi energy, and this we did here. And you see nicely that we also can see the Y point in this compound, which proves that this is a white semimetal with slightly doping of potassium. And here also we did the same. Now it's a hard magnetic material. We see also in the Hall a very nice hard magnetic hysteresis. of the compound. So this is the reason why we see the Weyl points also in upwards. We can magnetize it outside of this, the chamber, and then have a magnetized sample in the chamber. And also here we can see the anomalous Hall effect. The large value is related to intrinsic effects coming from the Berry curvature. So compared here, you see, this as a function of temperatures. This compound has one disadvantage. It has a TC of 200 Kelvin. It's not as nice as the Heusler's, but you see you have a Hall angle even of 20% and this small drop here, but this we can explain in this area. We assume skyrmions, so we are working on this too in this material. So it has real space and reciprocal space topology. Is a very nice material. And you see again, so compared to all the other magnetic material here, like the Hall effect versus the Hall angle, it stands out very similar, like also the manganese 3 compounds and so on. Okay, and again, we have a very large Nernst effect here now. We can make a hysteresis. Also here, it's at zero field, a large Nernst effect. This is nice because of the hard magnetic behavior of the material. And again, it's not comparable to the standard material. It's due to this extra contribution from the Berry phase, it's much larger, the value, compared to all the standard magnetic materials. Okay, so why did we do this two-dimensional materials? Okay, at the end of the day, and you saw this also in my nice ring, I want to have quantum effects. So we thought if we have a quasi two-dimensional material, we might can find a quantum anomalous Hall effect in this material. And some of you already know that there's this big family. So as you can have the Hall effect, the spin Hall effect, and the anomalous Hall effect, and gyro is also famous for the spin Hall effect. You can have also a quantum Hall effect, a quantum spin Hall effect, and a quantum anomalous Hall effect. And I'm sure you heard about the quantum Hall effect in the concept of the discovery of von Klitzing. So you have also this topological here two-dimensional edge states in a big magnetic field at low temperature in a two-dimensional electron gas. So if you destroy the sample here, also here, you cannot destroy the spin current around the sample. And the spin Hall effect even shows this effect without an external magnetic field, and this was invented by Molenkamp and Mercury telluride. And if you have a magnetic material, you suppress one of these topological edge currents, and you can have a quantum anomalous Hall effect. So we are looking for the quantum anomalous Hall effect in this material, and we even did a toy model calculation here with a tight binding model. So we looked what happens in a semi-metal if I go really to one layer, a thin film, and indeed this turns into a quantum anomalous Hall, a magnetic white semi-metal into a quantum anomalous Hall system. And we did some surface calculation of cobalt-3, tin-2, sulfide-2, one layer, and indeed we see some interesting edge states in this material. So we thought this is worth to try, but it's not as easy as graphene. We cannot scotch tape this material, so we simply work still hard on making it more 2D. But what we already saw is like, or see, if we simply think how big is the Hall effect per layer in our material, so we come very close to the quantized value of 1. So, and you can even see in the toy model, if you drive the Weyl points out to make this material insulating, you end up with a quantum anomalous Hall system. So this is already showing some evidence that even working harder on this material is worth to do. And we have convinced some of our SDM partners here, Vidya's group, but also in collaboration with Heims, to look then on our crystal maybe at the edges. And indeed, if you go at the edges, you find a chiral current here on the edges of cobalt, on a cobalt edge, you find a chiral current. And if you apply a biased voltage, you can really see nicely the quantization of the Hall plateaus in this material. So we think there is some evidence that we might find here a quantum anomalous Hall effect. Okay, so I am coming to the end, only a few words. So we try to do more two-dimensional material. We try to make Heuslers also dimensional, and this you can do if you go to this quasi-relatives from Heusler. This is a structure type which is called PbFCl. It's related to lithium iron arsenic, which is a superconductor. So we could find a material which is has a more two-dimensional magnetic structure, and this is this manganese, aluminium, germanium. And simply make a long story short, we find everything what we expect there. So we find here a very nice two-dimensional barrier curvature, surprisingly, which we haven't seen so nicely before. It's a nodal line metal. Luckily, the Fermi energy is slightly above the Fermi energy. Here we have also high TC, which we like more than the low TCs, and we see in APIS really here the nodal line point in this compound below the Fermi energy, and this is in nice agreement again with a large Hall effect, with a large Seebeck effect, in nice agreement with the DFT calculation and so on. Anyway, so this might be the material where we find a quantum anomalous Hall effect even at higher temperature. And with this, I come to my summary. So I hopefully showed you or convinced you that simply by doing a few transport experiments plus APIS and SDM, you can do very nice experiments on many magnetic materials. So I think crossing points in magnetic materials are quite common, and Gyro's group already contributed with his collaborators a lot, but they like more antiferromagnets and ferromagnets, I know. But I still like also ferromagnets. Okay. And I think this is a area where one could find nice materials for energy conversion, and I think one should look for oxides. Okay, and so our dream is a quantum anomalous Hall effect at room temperature, and okay, we also started some interaction with people where we do light matter interaction, and with this I'm happy. First, I have to thank my co-workers. So on the upper side, Julien and Hassan, my fantastic group with Jakob, who came from Gyro, okay, and Chaim, Beidenkopf, and Stuart Chaim for the SDM. Thank you very much. Thank you for your attention.
Thank you very much. Very big applause. Yeah. I think thanks for a very good talk. I must say your talks are getting better and better. You know, not that they were bad before, but it's really, really fantastic. So let's see. We have, I guess, please put your hand up or write your question if you like, and I'll look for you. The first question is from Pablo. So Pablo, go ahead and unmute yourself and ask your question, please.
Yes, thank you very much for the talk. It's really nice and informative. Actually, I have two questions. First question is about chiral anomaly. So I have noticed that the crystals have rather equal spatial dimensions. Therefore, usually it is assumed that they should be plagued by current jetting effects. Are they important in your measurement of the chiral anomaly?
So I think the current jetting is an issue, but especially in this crystals not, because the current jetting is an issue in bismuth, for example. If you have this super high mobilities, then you have current jettings. But in the magnetic materials, we have now one magnetic material which has really a super high mobility, lucky. So therefore, we always a little bit careful also with the chiral anomaly. But in this magnetic material, the current is so the current. So the current is not, or the mobility is not so high that we would have current jetting.
Time permits a small second question. How large are magnetic domains in these materials? Is there anything special in the structure?
I think the magnetic domains I showed for the cobalt 3, tin 2, sulfide 2, I think they are micrometer size domains, so they micron, so they are not special, I would say, from the domains. So it depends. If you have this very nice hard magnetic materials, the domains are larger if you magnetize them once and so on. So this is good for us. Okay, but I don't see some special behavior in the domains.
Thank you.
Okay. The next is Ralph. Go ahead, Ralph. Please ask your question. Can you unmute yourself, Ralph? Okay. You had your hand up. Not sure if it was meant as a question or not. Okay. It's not a...
Was not a question. Maybe I can say something about the domains, maybe because...
Yeah, go ahead.
So since the cobalt 3 tin 2 sulfide 2, and some of them shows also skyrmions, so I think, yeah, they have very interesting domain structure in this sense, and this a little bit hard magnetic material, they seem to be all very similar, like the antiskyrmions in the Heusler compound. So they turn into skyrmions, and the size of the domains are related in the thickness of the crystals, so they are even in this hard magnetic.
Sorry.
Okay.
The next question is from Ali Ibrahimian. Sorry. Can you unmute yourself, or should I read your question? Try to control it. Okay, this seems to be a problem with the microphone. So he's written the question down, so I'll ask the question. As the topology of some of these magnetic materials depends on the Hubbard-U parameter value, it seems that the topology of non-equilibrium electronic structure of these materials could be different in comparison with equilibrium ones. Is it possible to control the Fermi surface topology of these materials using laser photoexcitation, for example?
I'm sure, because I think, I'm sure, yes, I'm sure, therefore, I think this light matter interaction, which nobody more or less did, I would say, especially in this where Hubbard-U plays a role in this antiferromagnetic compounds and so on, I think there could be really interesting physics to come. Therefore, I'm also so keen that we find more oxides, for example. So like transition metal oxides and so on.
Okay.
So we are really, really interested in finding more correlated systems. And there are also a few, but so far everybody does a single particle picture work because it's very easy. So now it's time to do the correlated work, because also I think people start to try to understand topological behavior and topology with magnetism. This is quite new, and nobody knows what's coming out of this.
Good. Maybe Matthias, you can connect with the question.
Yeah, thanks, Claudia. It's really exciting talk. So, obviously we're all interested in these full Heuslers that, there's also experience in my group. And basically, both the anomalous Nernst effect and the anomalous Hall effect, originally one thought they would scale with the magnetization. And now, the anomalous Hall effect comes from the summing of the Berry curvature, and the anomalous Nernst effect was also measured in this cadmium arsenide and so on. So in your experience, for which materials do the anomalous Hall effect and the anomalous Nernst effect kind of show the same behavior? Like, are both large or both small? And when do you have differences that only one of them is large?
I think, as you see, that the anomalous Nernst effect is a derivative of the Hall effect. So what means the Nernst? I think the Nernst effect is the probability that you find an interesting effect accidentally is with the Nernst effect larger. Okay, but if you find a nice anomalous Hall effect and you don't see it in the Nernst effect, you simply have to slightly change the Fermi energy, and then you
to get the derivative large. Yeah.
I think I'm quite sure that this is a fantastic material for energy conversion, because you simply have to tune the properties accordingly to and the question is, theory should now predict what are the highest values you can achieve.
And so dope it essentially to move the Fermi energy up and down. Okay, thanks.
Sumit Ghosh. So Sumit, go ahead and, we can hear you. Go ahead and ask your question.
Sure. So I want to know, what are the main obstacles in observing a room temperature anomalous Hall effect? Or let's say, what are the electronic properties that will change drastically when you use a room temperature and reduce the corresponding Berry curvature?
I think you mean quantum anomalous Hall effect, right?
Yes. Yeah.
So anomalous Hall effect is observed at room temperature.
Sorry, yes, I mean quantum anomalous Hall effect, or let's say the Berry curvature.
The interesting thing is that the TC, if you see the anomalous Hall effect and the Hall angle, so I think it doesn't change so much with temperature. So I think, therefore, I'm quite optimistic. Okay, so which means if you calculate it per layer, so it's like, I would say it's like the tungsten telluride 2 is, okay, one obstacle is still, if you want to have the gap should be large enough that you have, it's like tungsten telluride 2. So in tungsten telluride 2, you can have a spin Hall effect up to 100K. So you need the gap, but the TC, to have a higher TC than room temperature is fine. So I think, yeah. Okay. I think it must be achievable.
So if the gap is more than, let's say, 100 MeV, we'll be quite safe there.
Yeah, and I have the feeling, therefore I have the feeling, I think even with topological material, oxides are an unexplored area. And the reason is exactly because oxides are lousily described with DFT. Okay, a single particle picture is bad. So, but we also know, if we want to have an inverted gap, okay, so we must have something which has a band dispersion of, if we want to have an inverted gap of 100 millieV, we must have band dispersions of more than an EV, you know, because you have to invert it and then you open up as a band gap. So the band dispersion must be much larger than the gap you get at the end due to the band inversion. So, but I simply think if you see oxides, you have the situation, okay? So we did this for barium bismuth oxide, where the Fermi energy is unfortunately not at the right position, but the gap is 0.7 EV, the band inverted gap. So it's possible, but simply we started now to do oxides, but you can do oxides one by one, one by one with very careful calculation. So then you need 100 students. Okay, they might calculate one oxide carefully per month, and again, it's not like 250,000 calculation for all the inorganic compounds. And you can imagine it's very difficult to motivate my theoretician to do it. No, they always think, why can we not do something?
Up to 250,000, I would say. Yeah. There's one more question from Kun Rong Yon, and he doesn't have a microphone, so I'll read the question. So do you think that there is any advantage of Heusler's compounds on various curvature materials for topological generation and protection of a spin polarized triplet Cooper pairs and Majorana fermions?
Yes, but I don't talk about it.
Okay, so she's not allowed to tell you. You may want to send her an email.
I simply think, no, I would be too arrogant maybe, but I simply think there must be topological superconductors, and there are a few nice superconductors, and we simply have to look for the right things. Okay, so I think there's a lot of interesting physics. I have the feeling coming soon. Okay. So I also think we have to find the right materials. Yeah. I'm optimistic.
Well, you're the material lady, queen.
Yeah, but I have now also fantastic physicists, I have to say, with Johannes.
Yeah, it's been amazing.
So he really find the right knobs to come to this. Anyway.
So I think that's all the questions for today. There was a very nice 400 people audience today.
Thank you.
So I think that's thank you. You're the popular one. Yeah, this is you're the star that brings them all in. So so thanks again, and we hope to see you soon here in your heart.
I hope too.
Where your heart resides. Yeah.
Also Burkhard and Matthias and so on. I really miss my crowd. Okay, I'm socially totally isolated here in Siberia. You see, I'm in Siberia.
So come and visit us, you know.
Come back, Claudia.
I have